reactors, commonly pronounced LIFTR, are nuclear reactors that use thorium in combination with fluoride-based molten liquid sulfur fuel. This type of reactor mixes its nuclear fuel directly with molten salt. To produce more heat for the production of electricity, the thorium in the fuel uses a reaction known as breeding. In this reaction, thorium-232 absorbs a neutron to start a fission reaction and become thorium-233. Thorium-233 only has a half-life of 20 minutes, but is extremely radioactive during this time. After emitting an electron, thorium-233 becomes plutonium-233. Plutonium-233 has a half-life of about 27 days, eventually decaying into uranium-233. What happens next is where the thorium breeding cycle gets its efficiency from. When the uranium-233 is struck by another neutron, the substance releases energy, along with releasing 2 to 3 additional neutrons. One neutron is needed to sustain a fission reaction, one is needed to continue breeding reaction, and another neutron can be used for the breeding. The breeding reaction leads to a seemingly unlimited cycle for the production of energy that can be converted into electricity.
It's not based on water cooling, and it doesn't use solid fuel. It's based on fluoride salts as a nuclear fuel. You have to heat them up to about 400 degrees Celsius to get them to melt, but that's actually perfect for trying to generate power in a nuclear reactor. Here's the real magic. They don't have to operate at high pressure. They don't have to use water for coolant, and there's nothing in the reactor that's going to make a big change in density. Unlike the solid fuels that can melt down if you stop cooling them, these liquid fluoride fuels are already melted. In normal operation, you have a little piece of frozen salt that you've kept frozen by blowing cool gas over the outside of the pipe. If there's an emergency and you lose all the power to your nuclear power plant, the little blower stops blowing, the frozen plug of salt melts, and the liquid fluoride fuel inside the reactor drains out of the vessel, through the line, and into another tank called a drain tank.
There are many reasons to use fluoride salts in a nuclear reactor. A LIFTR is a molten salt reactor that uses fluoride salts as a fuel source and cooling mechanism. As well, due to the ionic bonding of the salt, it is impervious to radiation and is very chemically stable. The salts require that they are above 350 degrees Celsius to be in liquid form, but once they are there, the molten salt stays liquid for up to 1000 degrees Celsius. It is important to note that these temperatures of fluoride salts still act under low pressure and remove concerns of situations that stem from pressurized reactors. Another helpful factor of the salts is that they stay at a higher volumetric heat capacity, which allows for less amount to be used for cooling than other coolants such as water.
In the design of a two-fluid molten salt breeder, the fuel salt mixture of lithium, beryllium, uranium fluorides is pumped through graphite tubes in the reactor core, where heat is generated by fissioning of uranium, and then through the primary heat exchanger, where the heat is extracted. The fertile or blanket salt surrounds the core where additional heat is generated. It is then pumped through the blanket heat exchanger, where this heat is extracted. The blanket salt mixture contains thorium, which is converted to fissionable uranium atoms more rapidly than they are consumed in the reactor fuel. The heat produced in the fuel and blanket streams is transferred by an intermediate salt heat transfer system to a supercritical steam-generating electrical system. In an alternative design, one salt containing thorium and uranium circulates through the reactor vessel and heat exchangers. This simpler single-fluid reactor is also a promising breeder if problems of on-stream fuel processing can be solved. ORNL studies indicate that molten salt breeder reactors should be able to produce electricity at low cost and with the high efficiencies of modern steam plants. Thus, the laboratory's important goals of nuclear reactor development converge in the molten salt breeder reactor. The search for a stable fuel at high temperature, the urge for fluid fuels, and the capability of providing an infinite supply of electrical power at low cost.
Molten salt reactors were first conceived in the 1960s when Oak Ridge National Laboratory constructed the first of this type of reactor. During the construction, the thorium-uranium breeding cycle became the focal point of supplying the reactor's main fuel source. In 1966, Oak Ridge finished the development of the molten salt reactor experiment, but after 3 years, the reactor was decommissioned because of funding. This was a result of the scientific community coming to a consensus of using uranium and plutonium as the main fuel source for nuclear reactors because of the understanding of these substances derived from the making of bombs and submarines. With the thorium molten salt reactors put on the back burner, the nuclear industry took off, using mainly pressurized water reactors. Until recently, there has been no research or use of thorium fluoride salt reactors. There are several key advantages to the use of lifters. One key aspect is the limited amount of waste produced in comparison to uranium or plutonium-fueled reactors. As well, the radioactivity is less toxic on the 10,000 plus year time scale. Another advantage is that this type of reactor does not use water as a coolant. This is an important factor when considering that all three major nuclear disasters have been caused from problems with water cooling systems. As well, thorium is about 3 times more abundant on the Earth's surface than uranium, and thorium is found next to many rare earth materials. This means that thorium is being mined with no plans of use. There are currently already tons of mined reserves for this fuel just sitting around. The future of nuclear energy will be the use of different fuels other than uranium, and thorium is the best element to substitute its use. The limited research for liquid fluoride thorium reactors means that the investment for making utility-scale reactor is uncertain. Although, there are plans for other countries such as India and China to begin implementation of this reactor. Lifters have many advantages over today's current pressurized water reactors, and a fuel source that is sustainable and far more efficient. This energy source has the potential to create electricity at rates that compare to fossil fuels at a utility scale.